Hello everyone, welcome to a new episode of Golang Cafe, and today we're going to talk about slices in Go. Slices are a very useful way of working with sets of typed data in Go, and are also known as arrays in other programming languages. Some people mistakenly use interchanged arrays with slices in Go, but we're going to see in today's episodes that they are different things, and although they are related, they have different behavior. In today's episode, we are going to see also how the append function and the copy function work under the hood, and we are also going to attempt to implement a very simple version of the append and copy function in Go, and we're going to see a few tricks and things to know about the slices in Go. Slices, before talking of slices, we should talk about the typed arrays or arrays in Go. The arrays in Go are a type, and you can just declare arrays very easily by just using, for example, the var keyword. You can use var keyword. You need to specify the length of the array using the square brackets, and then you can specify the type. In our case, we have an integer of 3 items. You can also do something different, like you can initialize and declare the array directly. So you have 1, 2, 3, and then you can declare the array initializing the values. You still need to define the number of items that you're going to pass in. Another option is to avoid passing the number of items and letting the runtime call count for you the number of items. So you just basically use the 3 dots to automatically count the number of items. And those are all possible options that you can use for declaring arrays. And the very unique thing about arrays and what makes them inflexible is the fact that once you define the length of the array, you cannot really change the length afterwards, so you cannot really change the type afterwards. So they're very inflexible to certain extents. Now we are going to print out the value of our arrays and whatever value they show us. So we have A, B, and C. And we're also going to see how we can change data. So we can easily change data just by directly addressing the array. So we can just direct addressing of the array and array definition. And we're going to see in a moment that when we declare an array and we don't initialize it, the values are going to be the 0 value of the type that you define. So in the first case, the 0 value for integer is going to be 0, and you're going to have all zeros for the length, for the number of times specified by the length of the array. So it's just 3 for this case. For B, we have exactly the same number of items as specified by the length, so you have 1, 2, 3 as expected. For C, you're going to have 1, 2, 3, 4. Then we do a direct addressing. We change a specific item in the array and we set that item to the value that we specify, and that's pretty basic, everyone knows that. Now, why there is a difference between the slices and the arrays? The slices, the arrays are not very flexible because, as we said, once you define the length of the array, you cannot really add more items or remove items for the array. Even if you remove item, you need to put a 0, so it's not very flexible in terms of the length of the array. Sizes, in the contrary, are very flexible because they are built on top of arrays, so internally they are represented as an array, and they have a starting pointer that represents the starting place of your array, and then it has a length which says how many elements are in the slice. It also has a capacity which allows us to say how many items are in the underlying array, and we're going to see in a moment how we can declare a slice. So declaring a slice is very easy, very simple. A definition. You can do that by, for example, S1. You can do by using the make keyword. But before using the make keyword, which is an interesting keyword that we're going to see, we can just do the same logic that we've done before. So you can just use integer 1, 2, 3. And the difference between the slice definition and the array definition is that in slice you don't specify the size. So it's the same as array, the only difference is that you don't specify the size, and that's a perfectly valid slice. And the other one that I was going to define was the one using the make keyword. The make keyword provides the same output as the one that we've just seen with the integer definition, but it allows us to have more control over the capacity of the slice and the length of the slice. So for example, the first arguments is the type of slices, so we say integer. You can store a slice of boolean, strings, bytes, anything that you want. We're gonna do integers for now. Then it takes an argument that is an integer that's representing the length of the slice, so how many items are currently in the slice. So let's say I want three items currently in the slice. It's going to be all initialized as zeros, obviously. And then it takes another argument, which is the capacity of the slice. So the capacity of the slice tells us how many items the underlying array can contain for this slice. So if we try to put more than 6 items in this case in the slice, we'll need to create a new slice because this one has a maximum capacity. We cannot really change the capacity easily of a slice. So we said that the slice operates using, it's just a structure that has three pieces of information. It's a pointer to an array item. Is a length that is an integer, so it tells us how many items are in the array, are in the slice. And the third argument is the third field is the capacity. The capacity just telling us how big the underlying array is, such that we are not going to overflow and are going to put too much data into the underlying array, and we're going to be able to then resize it afterwards. So if we want to figure out what the size and a capacity of a slice is, it's very easy. We can just use the len and capacity function, len and cap function. We're going to see it now. So we can just print that the capacity is going to be cap of S1, and the length is going to be len of S1, and same goes for S2. So we can do that for each slice that we want. And each slice is going to have a capacity and a length. The capacity again is going to be the length of the underlying array. The length is going to be the number of items currently in the slice, because the number of items currently in the slice is flexible. It depends on whatever you initialize it with or whatever data you put in the slice. And we said again, the slices use an underlying array. So underlying array would be something like this. It has 3 items, so it's defined as an array of 3. And you have 1, 2, 3. And same goes for our make keyword. The only difference with this case is that the underlying array is defined as an array of 6, where you have 0, 0, 0, all zeros basically, actually. You have all zeros in this case. The length of the slice is going to be just 3, and we're going to see that now. So you see S1 is capacity 3 and length 3. You have 1, 2, 3 as the items. S2 is length 3, so it's just 3 zeros, which is 0 value, and then capacity 6. We can put more items into the slice, the second slice, up until 6. Then once we reach 6, we are going to need to create a new slice with higher capacity. So we need to create a new array, allocate a new array with higher capacity. So the slice is just a syntactic sugar and a cover on top of the array that allows us to have dynamic sizing, but still has some limitation, because we have still a maximum capacity we can use. It's just very flexible because you can quickly resize the length of the slice, and we're going to see in a moment how. One of the operators that we use a lot is the slicing operator on slices. So slicing operator allows us to create a new slice from an existing slice by defining a range that we want to create the slice from. So for example, let's say that we have B1 is a new slice, and B1 is a new slice from the S1. So I just want to create, for example, item 2 and 3. I want to create a slice that is item 2 and 3. How do I do that? I use the slicing operator. The slicing operator, you just, if you are addressing with the square brackets, you put a colon, and then you have a lower bound and upper bound. The lower bound is inclusive, so you need to specify, for example, from item 1 up until item 3. The upper bound is exclusive, so it's going to go, it's going to pick item 1, item 2, and item 3 is going to be skipped, because obviously item 3 is the end of the slice in this case. And now we can just do exactly the same thing here. We can expect B1, and we see how B1 looks like. And this is very handy. This is very handy to create new slices. And the reason why it's very handy is because it doesn't allocate a new memory. It just uses the same array, underline array between the all slices. We're going to see in a moment how that looks. So we have B1 that has 2 items, 2 and 3, capacity 2 and length 2. So we see that it's pretty it's pretty easy to just slice a slice and create a new one. But the gotcha that you need to be aware of is the fact that when you use the slicing operator, be aware of changing items in the slice that are going to be reflected into other slices created from your original slice. So, for example, be aware of values changed that reflects via pointer, and I will explain in a moment what this means. So, for example, we have now the value as the item B1. So now, if for example I want to change the S1 at location 1 to be location 2, let's say S1 at location 2 to be 42, you would see that reflected into the B1. So B1, we didn't change anything on B1, but we changed an item on the slice S1, and the reason why the item changed is because we are using all the same array under the hood. Using the slicing operator means that we are using the same array for all these slices that we're going to create. So slicing operator, when using the slicing operator, all the subsequent slices use the same underlying array under the hood. So you need to be careful of that, because if you were to create a new slice again with a different range and you change the original slice, that will be reflected to all of your slices that you use with the slicing operator. So you need to be careful of that. The slicing operator is also used when you want to convert a static array to slice. So, for example, sometimes when working with cryptographic libraries, you will see that you have, for example, a typed key of bytes of a certain range. So, for example, you have a 32-byte key, and you, for example, need to convert that into a slice. Then the easy way to do that would be to just say to use the slicing operator. So in the slicing operator, in this case, you just pass no arguments, and that will just converts array to slice. That converts the array to a slice effectively. And then you can just do the same here. So you have key S key, which is going to be, by the way, just a set of 32 bytes. So just commit 32 zeros, and then the capacity cap of key S, and then the length as well, length of key S. So this is good to know if you ever want to convert an array to slice. So you're gonna see here cap 32, length 32, and that's the conversion. Now we said that when using the slicing operator, we are going to use the underline array. And a way to avoid this issue, that we are using effectively the same array for many variables, and we are basically using the same pointer to the array for different variables, and you're going to change the values everywhere. We need to copy the values, and for copying the values, it's very simple. You just basically for example, if you want to implement a proper slice copying, we just need to create a new slice and then copy all the values over, basically. So B2 make a slice of integers with a length of 2 and a capacity of 2, so we ignore that. Then we have we range over the S1. I just want to reset S1 again now. It's going to be 1, 2, 3. As we said, we range over S1, and B2 of I is going to be equal to S1 of I, and then what we do, we just print what we created. So this will not change the values. If we change values in S1, B2 will not change any value. The values in B2 will not change because they are not pointer to the value, but are just copies. So S1 we need to just override it. And we need to copy the length of S1. Obviously, if you just want to copy a portion, you can just put a for loop with the portion that you want to copy. So B2 is 1, 2, 3, cap 3, length 3. Now, if we were to change again S1 of 2, and we want to change that again, B2 wouldn't be affected by that change, because we are not using the same underline array. We are just using a copy of the data. So this is very effective when you want to copy the data and not have side effects. To avoid side effects, instead of using a slicing operator which shares the underline array, just copy the entire slice to a new one, and that will do the trick. It just copies all the data over, and then you don't have side effects, because when you slice slices and you change the values, you will have side effects. Now, very interesting point is the fact that this for loop that we have made here is also implemented in something that is called the copy. So if you use the copy, you will see that you can just do something like this. You can just call the copy keyword, and that will copy the values. You would see that all the results are the same. So the copy keyword is just a way for copying the values. And the way that the copy keyword is implemented is very easy. It's very simple. So we can just implement that copy integers. So it's just a slice. As destination and source of integers, and returns the number of also returns the number of copied bytes or copied items. So we have n of integer, and then we have I, e, range over source, and then destination of I is equal to source of I, and then we just return n, and we need to obviously we need to increment n whenever we copy something. And that's the same. As you can see, the same result yields the same result. Same as copy, which you can see from cdoc at godoc built-in copy. Same as copy function. This is very handy for copying slices over from a place to another. So this is the way that you can copy slices from one place to another. That's very easy. Now, how do we add the items to a slice? The way that we add the items to a slice is by just using the slicing operator effectively. If we use the slicing operator can be used to create the slices with the bigger length up until the capacity of the slice. So, for example, we know that for example the slice S2 is a capacity of 6 and a length of 3. If we want to add a new, so S2, let's say that we redeclare it again, you override it. So we have a size of 3 and a capacity of 10, for example, let's say. So if we want to increase the length of S2, just use the slicing operator. It works up until the capacity of S2. obviously. So if you are trying to slice something that is more than the capacity, you will get a panic. So if we want to increase the length, so what we can do, we can just say s2 equal to s2 slicing from the beginning up until you know, the new length. So instead of 3, let's say I want to length of 5, and then we can just actually leave it there like empty, and then we can just print it out. Let's see where the s2 is, and you will see now in a moment how this play out. This is the default size and capacity. So the S2, the first time S2 is a length of 3, capacity is 10, and length is 3. And the second time we just increase the length by using the slicing operator, and increasing the length with the slicing operator just increases the length and keeps the capacity to 10. Now, if we want to add new items to the slice, it's very easy. You can just implement a method that allows us to use the slicing operator, check if the capacity is what we expect, and using the copy to copy items that when you slice if the capacity is more than what we expect, and we can do that very easily. So we can implement an append function for the slice, and we can specify that here. So the slice of integers, we have an element, and this returns a new slice. The thing that we need to check is the expected capacity. Expected capacity is the length of the slice plus plus 1, which is the element, obviously. So just one element. If you had more than one element, it would be length of n or v. But for the sake of testing, we just say that we just have 1 for now. So it's fairly easy for us to see and to check. So if now the capacity of S, if the capacity of S is less than expected capacity, it means that we need to resize to grow the slice, and this means that this new allocation, create a new slice from scratch. New allocation, create a new slice from scratch. And how do we do that? New slice is just using the make keyword again. The length of the slice is going to be the expected capacity, because we are the expected capacity because we have the length plus 1. So the length plus 1 is the expected capacity, at least the expected capacity. I think this I should call this not the expected capacity but the expected length, because that's what we need, the expected length. The expected capacity can be even more. The final capacity can be even more. The expected length. And the capacity, we are going to use double the capacity that the slice has. So I'm going to use double the capacity that the slice has. Sometimes you will see capacity plus 1 multiplied by 2 if the capacity is 0. So it's good to have if the capacity is 0. And now we need to copy. All of the data from the old slice up to the new slice. So new slice of I is equal to S of I. So copy the data. Oops. Copy the data. Create a new slice. Copy the data from old to new. Assign new to old. New slice. Grow length. Now is grow the length of the slice, and the length of the slice is just s up until expected len. Return s. So now if we go here, so let's say that we have now s2 equals to append int s2, and we have 31. We need to define obviously expected length. So it's expected length. We obviously we have to assign we grow the length and we assign the item, the element, obviously. which is the current length. The current length now is already increased, so it's current length minus it's expected length actually minus 1 equal to element. So we see that length before was 5, length now is 6. Now let's use something more clear because we have a lot of zeros here. So if we, for example, we say that we have a again we have S1 with 3 items, and we're gonna see that 1, 2, 3, and then we have S1 append 31 S1, and this is also going to it's going to increase the capacity of S1 because S1 has 3 items and a capacity of 3 as well. So you're gonna see that it's going to increase the capacity. Obviously, we need to specify as a slice, not as an array. So you see, the first time we declare S1, capacity is 3, length is 3. Second time, after we append, capacity is 8, length is 4. Capacity is 8 because we went capacity plus 1 multiplied by 2, and that's why it's the capacity, original capacity was 3, plus 1 is 4, multiplied by 2 is 8, and the final length is 4. So you see 1, 2, 3, and then 31. And that's how the append function works under the hood pretty much. In the append function, we can also apply a syntactic sugar and something that we already implemented, which is the copy function. So here, copy int, destination, and source, and that's pretty much the same. As you can see, that's pretty much the same, and that also tells us that the slices are actual pointers. So the slices behave like pointers. You can see that we are not passing explicitly a pointer, but the data is being changed automatically because the underlying array is a pointer, so the data is not lost when we copy. We call a function and we copy the slices and so on. So that's pretty much the append function. The only difference between our implementation and the runtime implementation is that the runtime implementation is going to have much more extensive logic for us to check all the types and apply to all the types. You can actually check the implementation if you go into runtime slice.go. You will see that the slice, the definition of the slice is a length, a capacity, and an array, a pointer to an array. So it uses a pointer, unsafe.pointer, which is just a way of working with pointers from within the Go runtime. So it points to an array, and it specifies a length for the slice and a capacity that represents the length of the underlying array. And if we want to see the make functionality that creates the slice, you can just search something like make slice, and that make slice will take care of creating a slice from scratch. So it takes a type, so it takes whatever type we are trying to initialize for that specific slice, the length and the capacity of the slice. For a type, there is a specific size. For example, an integer is going to take a different amount of memory than a string, or than a float 64, or than a boolean. So each type has its own memory footprint, and that's used for calculating the memory footprint. As you see here, it's returning the memory footprint for the slice, for the entire slice. There is just some checks on overflow, and then the ultimate log GC, which is going to do the allocation of the slice memory needed for the slice effectively. And same goes for the grow slice. So the grow slice is what is used for the append function. It says grow slice and slice growth during append. It is past the slice element type, the old slice, and the desired new minimum capacity. And so you will see that it has the slice, which is this pointer to type. So it's just a metaprogramming way of saying any type of slice, whether it's integer slice, string slice, boolean, and so on and so forth. And here is the logic that we also implemented, that it uses the multiplication by 2. This is just doing new cap plus new cap, which is using the old cap summed together twice. And if that's not enough, it's going to do some checks. If obviously it's going to use the double capacity if the number of items is less than 1024. So if we have a slice with 1000 items, it's going to double the size. If the slice has more than 1024 items, it's going to grow the number of items by a quarter of the size, because otherwise it's going to, each time we reallocate the slice, it's going to be huge reallocation. So it just goes 25% of the capacity. So instead of, let's say that we have a slice of 2000 items, instead of the 2001st item, instead of having a slice of 4000 items, we have a slice with 2000 multiplied by 25% effectively. So that's pretty much the logic. Then here there is all logic around calculating how much memory the capacity needs for each type and so on and so forth. But it's not something that it's particularly interesting for us to see. So the grow slice, we've seen the grow slice, which is using the append. We have seen the make slice as well, which is used when we created a slice. We have seen also the slice definition in the runtime. So it's just using an array under the hood, and the length and the capacity. And we have also went through a couple of examples on how to use the slicing Go and how to use all the slicing operators and all the tricks and things to know about slices. I hope you liked the tutorial, and see you on the next one.